Hi, this is the beginning of Chapter 5. I'll split it up into two separate screencasts. So the first thing is, what is energy? Energy is the capacity to do work and transfer heat. And when we're talking about heat in chemistry, we refer to it as thermochemistry. And thermochemistry is the study of heat flow in a chemical reaction. And so this part of my lecture is going to help you with the lab that you're doing, the first lab that you're doing on the specific heat of a metal. And it's important to be able to define your system and your surroundings when you're talking about heat flow. So in the lab that you're going to be doing, you're going to identify a metal that you'll choose from the menu, and you're going to give it a temperature, a high temperature. So if we were doing this in the lab, we would put the metal into a beaker of water and heat it up, probably to 100 degrees Celsius. So in the lab, you want to use a fairly high temperature of your metal. You won't be heating your metal in a beaker in the virtual lab, but you'll be able to identify a temperature of it. So your system that you have that's hot is holding a certain amount of energy. Then when you take that hot system and you place that system, which is our metal, into a, let's say, room temperature beaker of water, the heat from that metal is going to get transferred to the surroundings, which is the water. So the system absorbs heat, and when we place it into the room temperature water, the system will release its heat to the surroundings. And we define that heat flow, or we identify that heat flow as Q. For the system, it's going to be positive. It takes energy in. Again, in the lab, you're not going to be heating it up. You're just going to identify how hot it is. And then so then your system ends up releasing its energy. And when it releases its energy, it's going to have what we call a negative heat flow. So when it takes energy in, it's positive Q, which is an endothermic process. And when it releases its energy, it's considered an exothermic process. That's what this is supposed to say right here, exothermic. Okay, so just a couple other examples. If you take ice, H2O solid, and you have to add energy to it, if you add energy to it, it would turn into a liquid. So if you heat it up, it's going to turn into a liquid. And so we call that process an endothermic process because it takes energy in. The Q for that, and Q is the variable that we use to describe heat. And heat flow away from the system is negative, into the system is positive. Another example of where we would use Q is in a chemical reaction where, let's say, we burn methane in the presence of oxygen. And what happens when you burn methane? Well, energy is released. And so that's where we would see Q as a negative value. Okay, sorry, squeezing it in there. All right, so heat flow changes the temperature of the system. Right? That would make sense, right? If the heat is flowing, heat is moving, the temperature of that system will change, as will the temperature of the surroundings. So how do we measure the heat flow? Well, it's with this equation. It's Q is equal to C times delta T. And capital C is what we call heat capacity. So it's whatever that whole system is. Is it a tiny, tiny little pellet of copper, or is it a large chunk of copper? It depends on whatever the size of that material is. We define that as the heat capacity of the system. And the units are going to be, for Q, joule. Heat capacity is joule per degree Celsius, and the change in temperature is degrees Celsius. Now, for a pure substance, we're going to look at this equation a little bit differently. We're going to look at it as Q is equal to little c, which is called the specific heat. All right, sometimes your book refers to it as the specific heat capacity, not to be confused with heat capacity, which is a capital C. And in this case, you multiply that small c by the mass times the delta T. In your lab that you're doing, you're going to be identifying the small c. So this small c, which is called specific heat, is an intensive property, which means that it can be used to help identify a substance, which is one of the tasks in your lab. So what does it really mean? If we have a large specific heat, and SH just is an abbreviation for specific heat, it means that it absorbs and holds a lot of heat. So let's say you wanted to heat water in a stainless steel pan. That the point of that would be that if you wanted your water to get hot, and not necessarily the pan, you don't want all of your energy to go into the pan, you want it to go into the water, then you're going to want to use a material such as stainless steel, which has a very low specific heat, roughly 0.5 joule per gram degrees Celsius, while the water has a very high specific heat, which is 4.184 joule per gram degrees Celsius. So significantly different values for specific heat. And so if we want the water to be the one to be taking in the heat, you want the pan to heat up easily and then pass its heat off to the water. So that's what it means. So if you think about water, and its specific heat is a very, very high value. The water is, because it takes water a long time to heat up and it takes it a long time to give off its energy. While something like stainless steel has a specific heat that's very low compared to water, that would heat up quickly and give its energy off quickly. Something like copper, I'm going to guess here, it's right around 0.3. So 0.3 would be even a lower value of specific heat. It's a material that would heat up very quickly. Okay, I'm going to go on. All right, so here's what we know, that in calorimetry, the Q of the reaction that's occurring is considered a negative Q of the calorimeter. So in other words, what's happening in the water is opposite to what's happening with the metal, which is what you're seeing in the lab that you've either started performing or are going to perform. So the equation that describes that I like to use, that I put in your pre-lab notes on the lab, is that the Q of the water is equal to negative Q of the metal. So what that means is that if the heat is leaving the metal, it's going into the water. Leaving in chemistry, whenever anything is released or leaving, we give it a negative value. It's kind of a convention in chemistry. Release is always negative and a gain is always positive. So when the metal releases heat, it would have a negative Q. When the water gains heat, it would have a positive Q. All right, so if we wanted to take a look at a chemical reaction, that's occurring in a coffee cup calorimeter. Calorimeter, if I have a particular calorimeter that contains 50 grams of water at 100 degrees Celsius, when 1 gram of calcium chloride is added and the temperature increases to, I'm sorry, some of this printing is kind of light, to 28.51 degrees Celsius, then calculate the Q of the reaction. So just like we had with the simple calorimetry of the metal in the water, what happens to one, the opposite happens to the other. The same thing is true for the dissolving of calcium chloride. We'll say the Q of the water is what happens to the water, and just the opposite is what the reaction is. So the only thing that we can measure is what happens to the water. So if I have 50 grams of water and I use the specific heat of water, which is a given quantity, and I find the delta T of the water. So remember this expression of delta T is always going to be T final minus T initial. And you have to use delta T that way in order for your signs to calculate out correctly algebraically. So in this process, what we come up with here is a Q value that's positive. All right, so our Q value is positive here, the Q of the water, because 28 minus 25, I'm going to end up with a positive value on this side. So the Q of the reaction is negative. So then what I can say here is that if the Q of the reaction is negative, then I have what's called an exothermic process. Okay, so we're going to be looking at the two different processes. It's either an exothermic or an endothermic. And in this case, since we're trying to identify what the reaction is or what the dissolving process is, we see that because the change in the water temperature is positive, then the change the Q of the reaction has to be opposite that. So what happens is if we take calcium chloride and we put some calcium chloride pellets into a beaker of water, as those pellets dissolve, they release their energy to the water. That's why the temperature went up from 25 degrees Celsius. Okay, and then there's, I just want to make sure it's clear what the difference is between the little c and the capital C. Just go back here because there are some distinctions between those two. So if I'm using little c, as I am in the lab, then I need the mass of the material. So in this equation, the little c times the mass times the delta T gives you the Q. In this equation, if the problem, this isn't what it is in the lab, but if your problem gives you the heat capacity, it's already including the mass of the material, and the calculation really becomes the same calculation. Okay, I hope that's clear. Sorry for jumping back there. And then the only other thing with calorimetry is what we call bomb calorimeter, because not all reactions can take place in a simple coffee cup calorimeter, and they need something a little more high-tech called a bomb calorimeter, and these are used for reactions that produce very high temperatures. And so all the heat that's given off is given off to the water and the bomb calorimeter. So the equation just looks a little different. It's going to be the Q of the reaction is equal to negative Q of the bomb plus the Q of the water. So you not only include the piece that we were just talking about for the Q of the water, but you also have to include the Q of the calorimeter, which would be the specific the heat capacity of the calorimeter, which would include the mass of the calorimeter and the change in temperature. The change in temperature here is the same as the change in temperature here. Okay. And then this here, I'll just let you look through this. I won't spend the time on it right now. It's just an example that will walk you through a calculation for the bomb calorimeter. But that's it for this piece, and I'll be back in a minute.